Welcome back. In today's session, we will be discussing few problems with respect to the DH representation on a given robotic structure. First example, let us look to the first example. For the given simple 2-degree of freedom planar robot, derive the forward kinematic equations based on DH representation. So in this figure, you can see a 2-degree of freedom planar robot where there are one joint at the base and the other one is at the shoulder, and at the end side you are not having any gripper. So this is one of the configurations where you are only having specific joints, but there is no end gripper. On the end gripper point or at the end of this particular link, you can connect any type of wrist or any type of end effectors or tools with respect to your applications. Okay, so let's get into the derivation. So in order to start with the DH representation, let us recall to the previous classes where we have seen that the basic step for starting with DH representation is to identify the joints. So in this given example, we will be starting with that. Okay. Then once the joints are identified, then we need to identify the links. Then we need to assign the x and z axes for each of the joints. Then we need to start with one of the joint with respect to the reference. Again, so if you recollect in the last session, I have mentioned that when we move on to the real 2-degree of freedom planar robots, always we need a reference axis. Okay, so in this case we will be using this as the reference axis. That is, the world reference axis is taken as a reference for assigning the x and y axis directions for each of the joints. Okay, so the first task, assign the joints. So there are 3 joints for this. Actually there is no joint at this point, but we are assuming that our transformation, we need the DH representation for the transformation of this robot from this fixed point up to this point at this space where we are supposed to fix the end gripper or the tool or any other wrist. Okay, so the first task is been completed. We have assigned the joints joint 1, joint 2 and joint H, that is the end gripper or the final point. Then second task for any DH representation is to assign the link. So we have identified that between joint 1 and joint 2 you have a link. So you have assigned that link 1, and between joint 2 and joint H where there is no actual joint, but we are assuming that there is a joint, so that when we need to describe its motion for the base, from the base to the end gripper, you can use this. Okay, so here it is link 2. Now moving on to the x, y and z, or x and z axis assignment. Here you can see that z is been assigned in this direction and x is been assigned in this direction. This is for the universal reference frame. So we will be taking into reference these directions. Okay, so starting with joint 1, the first joint has the z axis assigned in this direction, which is parallel or which is in the direction of the universal frame. There may be a small variations in the variations, that means it may not be purely parallel, but it is direction in this particular direction. And joint 2, and for first joint I have assigned the z axis, and since this joint is a pure revolute joint, there is only one joint variable defined as theta. Okay, so as per the rule, the z-axis of joint 1 is designated as z0, and the joint variable for joint 1 is designated as theta 1. So moving on to the second joint, so for second joint the z-axis is designated as z1, again parallel to z0, then its joint variable is designated as theta 2. Now going to the third joint or the end point where I am designating that particular joint as ZH, that is my destination. I need to derive the DH representation for the transformation of this robot from this joint Z0 up to ZH. So I am giving it as ZH here. So I have assigned the Z axis. The next task is to assign X axis. So before that I can see that between joint 1 and joint 2 I have the link. which where the link length is a1. Okay, so the x-axis. Okay, then between the joint 2 and the joint H, I have the link with a distance of a2. So this is the distance of the common normals. Okay, so the distance between two adjacent z-axis is defined as the common normal as per the definitions in the previous class. So here I am assigning that first the common normal or the link distance between joint 1 and joint 2 as a1, and between joint 2 and joint H as a2. Now coming to the x-axis, when I am considering this joint alone, joint 1 alone, you can see that this joint is fixed to the ground surface or the universal reference frame. So the x-axis will be in this direction. Okay, so I am assigning the x-axis corresponding to joint 1 as x0. Okay, now coming to joint 2, when it moves on to joint 2, in this case it will be along the direction of the common normal. Okay, so for joint 2, the x-axis will be in the direction of link of the common normal between joint 1 and joint 2. Okay, similarly, when we move on to joint H, the x-axis of joint H will be in the direction of the common normal between joint 2 and joint H. So by this I have assigned the x and z axes for each of the joints in this for the given 2 degree of freedom planar robot. Now let's move on to the derivation of the DH parameter table or filling of the DH parameter table. Okay, so this is the figure which we have right in our hand. So let us start our derivation or our filling of the DH transformation sequence or the DH parameter table. First, let us consider only the joints 1 and joint 2. That means what are the values for each of these DH parameters when our robot frames transforms from the point joint 1 to joint 2, that is from x0 z0 axis to x1 z1 axis. So the first step in transformation is to make the x0 axis parallel. Okay, so in this case you can see that x0 is in this direction and x1 is in this direction. So in this case, first of all, I need to keep the z axis as a constant, and I need to rotate the joint 1 by an angle of theta 1 so that x0 will be in parallel to x1. Okay, so I am rotating this joint alone by theta 1 with respect to or about the z axis, so that now I got x0 and x1 parallel. Then so that is I need to rotate by theta 1 with respect to z. Okay, the second step in DH representation is I need to make this origin. Okay, I need to coincide what I need to make the x0 and x1 coincidentally or aligned. So here you can see that after rotation itself both are lying in the same line, so there is no need of the step 2 in our DH representation. So the third step we move is that we will be moving this, we will be making the origin of the first frame x0 z0 frame in linear or aligned with the origin of the x1 z1 frame. So I need to move this entire structure entire frame towards this origin by a link length of a1. Okay, so I am moving this together to z1 x1 by a distance of a1. Okay, now I can see that the origin of x0 and z0 and the origin of x1 z1 are aligned. Both x1 and x and z axis are been aligned, so there is no need of further transformations. So what are the sequence of transformations in between joint 1 and joint 2? First of all, I am rotating about z axis by an angle of theta 1. Then I am transforming in the x direction by a distance of a1. So for the transformation from 0 to 1, I need only these two parameters. Okay, now let us look to the next set of transformations, that is from joint 2 to joint H. So in this case I am having the x1 z1 right now and xh and zh right now. So in this position the first principle is to align the x1. Okay, first principle is to align the x1 x axis. So I am going to rotate the x1 alone because I need to align this x1 to xh. Okay, so I am going to align x1 alone with respect to z by rotating an angle of theta 2. Now I can see that my x1 and xh has been aligned. Now I need to bring the orientation of z1 x1 frame to zh xh. So I need to transform by linear distance of a2, that is my link distance. So at the end of this I can see both x1 z1 and xh zh frames are aligned with respect to origin as well as with respect to the x and z axis. So the transformation sequence is theta 2 for theta. There is no transformation d because we are only having revolute joints, so there is no d parameter because d parameter corresponds to that of prismatic joints or prismatic movement of the joints. Then a is the distance of link, so here I am having a1 and a2. Then alpha is the alignment difference between the two z axes, but here you can see there is no need of aligning the z axis. Immediately after applying the sequence you can see that both x and z has been aligned. Okay, so now to derive the transformation equation I am having the table like this. So for transforming my robot frame from position 0 to position 1, that is from joint 1 to joint 2, I need to follow a rotation of z axis, a rotation of theta 1 about z axis multiplied by a translation of a1 along the x axis alone. So a1 comma 0 0 to transform my robot given planar robot from joint 2 to joint h. Okay, I need to 0 to 1 and 1 to h. It is not 2, it is h. Okay, so to h I need to rotate the by theta 2 about the z axis, then followed by a translation of a2 comma 0 comma 0. So to obtain the entire transformation equation from joint 1 to joint h, that is marked as 2 here, I need to multiply these two integral transformation equations, which gives me rotation of about z by theta 1 multiplied by translation of a1 comma 0 comma 0 multiplied by the second transformation set of equations, rotation of theta 2 about the z axis multiplied by translation of a2 comma 0 comma 0. Now on expanding I am getting this 4 by 4 matrices. Now on multiplying and solving I will be getting a final 4 by 4 homogeneous transformation matrix corresponding to the transformation of the given 2 degree of freedom simple planar robot from the joint 0 or 1 to the joint h as marked in the figure. Okay. Thank you. So in the next section we will be discussing another example of DH representation.